Our objectives for today are to avoid some common misconceptions about not only trig functions but functions in general. We want to observe the derivation using geometry of a key identity that we're going to use again and again to help us come up with other trig identities as well as use it in other calculations. And then you're going to use that identity today and also in class to come up with some other identities. And I think that's the key to this whole unit, is if you can memorize only the key identities, then use those to come up with others, you'll have a lot less strain on your mind to remember the large amounts of identities that we actually have in this unit. Okay, so let's start with a little exercise in the calculator. I have put my calculator in radian mode, as you can see, and I'm also in exact mode. So when I type in any trig value, I'm going to be getting an exact answer. Now, we've been studying the unit circle, where you have some key angles that we use geometry to determine these ratios of sides, pi over 6, pi over 4, pi over 3. There are many other values on the unit circle, obviously. We've been using a calculator to come up with them when they're not familiar. When I type in the cosine of pi over 12, it turns out I get a nice answer. The square root of 3 plus 1 times the square root of 2 over 4, or the square root of 6 plus the square root of 2 over 4. So this is showing you that there are other angles that have nice trig ratios. And I think the question today is, where does this answer come from, and could we have done it by hand? So we'll come back to that idea throughout the lesson here and see that that is actually possible to do. Alright, I'm going to take you through a short PowerPoint here. And we started with the cosine of pi over 12. We are now in the second day of trig identities. Things are going to get a little bit more advanced here. But we're going to start with a little Bible passage that's going to be a parallel for what we do today. So, no longer shall your name be called Abram, but your name shall be Abraham, for I have made you a father of many nations. A little picture of Abraham about to sacrifice Isaac before the angel stops him. And so, what you're going to see today are what we have referred to the last 5 years as the mother and father of many trig identities, because from the two that you learned today, we will develop many, many others. And I think if you remember the key figures, if you remember Abraham and you remember Sarah, then the other ones come pretty quickly. So the identity that we refer to as Abraham is this one right here, the cosine of an angle A minus an angle B. What is this the same as in terms of trig functions? How is this done, etc.? First of all, we need to come up with a little agreement here that the cosine of A minus B is not the cosine of A minus the cosine of B. This is the misconception I referred to in the objectives. And this occurs every year. Students want to do this because it's convenient and it looks similar to something you've done before. It looks like distribution. Okay, but you got to remember, you only distribute when you're talking about multiplication. And we're not talking about multiplication when we're doing trig functions. But let's just test one set of values for A and B to show you that this is not true, and hopefully you'll never even think about doing it again. So let's test pi over 3 for A, pi over 6 for B, and see what happens. Okay? So I plug those numbers into both sides of that false equation, and I'll show you that we get two different answers on the left and on the right. Okay? On the right, the cosine of pi over 3 minus the cosine of pi over 6. Those are nice values that we know. So we get 1/2 minus the square root of 3 over 2. Turns out that pi over 3 minus pi over 6 is pi over 6. And we know the cosine of pi over 6. It's the square root of 3 over 2. These are not the same number. Therefore, with one counterexample, I have shown you that this statement is not true in general. It may be true for certain values of A and B, but we can't say it's true always. And just as an aside, I want to ask you a question, rhetorically of course. Has this idea ever worked with functions? What do I mean? Have you ever been able to distribute functions over addition or subtraction? Did it work with the square root? No, it did not. Did it work with the exponential function? No, it did not. Did it work with the natural log function? No, it did not. Did it work with exponents? This is the one we're probably the most guilty of, right? We do this all the time because we're not thinking clearly about things. You can't do it here. Did it work with fractions? Can you split up a denominator like this? No, you cannot. So in general, you don't take a function of a sum or difference and distribute the function. Okay, it does not work in general. So it's not going to work here, and it should not be a big surprise that it does not work. So that brings us back to, okay, if that doesn't work, then how do we do it? We're going to take you through a little geometric demonstration here. This is the unit circle. So we know that 1, 0 is a key point on the unit circle. I'm going to draw an angle in standard position and call it angle B. And that means that the coordinates of this dot on the unit circle, this point, are the cosine of A, comma, the sine of B. Because that's how we have defined trig functions for angles past 90 degrees or past pi over 2 radians. Okay, I'm also going to draw a second angle in standard position, this black angle, and call it angle A. The coordinates of this dot in the unit circle will be cosine of A, comma, the sine of A, therefore. Now, it is possible, with a straight edge and a compass, to construct an angle such that, okay, that this little piece here between the black and the orange, that angle there, is congruent to angle B. Okay, that is possible to do. I'm not going to take you through that construction, but it is possible to make these angles right here, okay, this angle here and this angle here, congruent. That being the case, how long is this orange angle? What would we call it? Okay, well, it's not quite all the way to A, so it's less than A, but how far less than A is it? Okay, well, it's B radians less than A. So this orange angle is going to be A minus B, which means that the coordinates of this dot up here are going to be cosine of A minus B minus the sine of A minus B. Now, some geometry for you. Just to review, if this angle right here is the same as this angle here, then these arcs that are created by the angle are congruent. So these things are going to start to disappear here. So I'm going to connect now the 2 points that create the 2 congruent arcs. Okay, so this arc right here that goes from cos A sine A to cos B sine B is congruent to the arc that goes from cos A minus B to sine A minus B. And there's a theorem in geometry that says that if the arcs are congruent, then these chords have to be congruent. That lets us set up a distance relationship between these 2 chords. Okay, it says that the distance between these 2 dots is equal to the distance between these 2 dots, which gives us this equation, which we're going to solve for what? For cosine A minus B, right? The identity that we're looking for. Now, this is going to be a lot of algebra, but nothing that you haven't seen before. There's going to be a lot to write, and in the end, you're going to get something pretty nice, believe it or not. First step here is going to be to square both sides to get rid of these radicals. Okay, that's what it looks like. Now, you have 3 binomials that are being squared, and on the right side, this is just one expression that's being squared. So we're going to start with the left side. We're going to expand both of these binomials, and we get all this stuff. And we look through all that stuff, and we start to see some things. Okay, if I see cosine squared A added to a sine squared A, I get excited, because that's going to be a 1 by the Pythagorean identity. Cosine squared plus A plus sine squared A equals 1. I also see a cosine squared B and a sine squared B. That's also going to be a 1. So, combine those. We can rewrite the left side a little bit simpler. And now we have 2, still have the minus 2 cosine A cos B and the minus 2 sine A sine B. Now we'll look on the right side. We need to expand this binomial. So when we do that, we obtain what we see here. And again, we get excited because I see a cosine squared A minus B and a sine squared A minus B. Those can be combined to be a 1 by the Pythagorean identity. Combine that with this other one, and we now have 2's on both sides. Those can be canceled out. And now every term on the left and every term on the right has a negative 2. So we can cancel negative 2's. And look what you have left. On the right side, you have cosine A minus B, and on the left side, you have a nice expression in terms of only cosines and sines of A or B, which is what we're looking for because we're assuming that we can figure those values out. Okay, so in the end, this is what we have. And this is the identity that we refer to as Abraham. This is one to memorize because we're going to use this to come up with many others. So what do we got? The cosine of a minus b is the same as the cosine of a times the cosine of b plus the sine of a times the sine of b, right? Nobody would ever have thought that just looking at it. So it took some geometry to come up with. Now, let's first use this to figure out the cosine of pi over 12 exactly by hand. Okay, turns out that pi over 3 minus pi over 4 is pi over 12. So that means we can use this identity with a being pi over 3 and b being pi over 12, or sorry, pi over 4, to come up with the cosine of pi over 12. Substituting these values in, here's what we get. Cosine of pi over 12, which is what this is equal to all this stuff, and these values we know from the unit circle that we've memorized. So we have the cosine of pi over 3, which is a half, times the cosine of pi over 4, which is the square root of 2 over 2, plus the sine of pi over 3, which is square root of 3 over 2, times the sine of pi over 4, which is the square root of 2 over 2. Okay? And if we combine those together, we get the square root of 2 over 4 plus the square root of 6 over 4. And if we go back to the calculator, look what we have. Square root of 6 over 4 and square root of 2 over 4. So there was a way to come up with that by hand. We had to use this special identity, and that's just one use of it. Here's another use. Okay, we're going to get to the point where in class we're going to use Abraham to come up with many identities, but you're going to start it off here in your entrance ticket. Okay, so first of all, recall that we have an identity that says the sine of theta is equal to the cosine of theta's complement, pi over 2 minus theta. That's a cofunction identity. So we're going to use this to come up with Sarah. Okay, Sarah we refer to as the sine of a minus b. Okay, so you have Abraham, you have Sarah. We're going to use Abraham to derive Sarah here. Now, what would this be equivalent to? Well, by the cofunction identity, it would be equal to the cosine of pi over 2 minus this angle here, okay, a minus b. And I'm just going to rearrange some things on the right side here. You'll see why. I'm going to use a bracket this time. So I have the cosine of pi over 2 minus a minus negative b. Okay, let's agree that this is correct. Pi over 2 minus a, that's right there, and then minus a minus b. It's really a plus b, but if I write it this way, it's okay. And so what am I going to do with this now? Okay, well, what you're going to do is you're going to work with this right side because you can use Abraham 2 times. Okay, one time with these two angles, pi over 2 minus a and negative b, and then the second time with pi over 2 minus a. And you will eventually come up with the identity for sine of a minus b, which is what you're after. And those are the two identities we're going to use all day in class on Wednesday. Now, along the way, I'm just going to remind you, you're going to need 2 identities that we did last class. You're going to need the odd and even identities for sine and cosine. Okay, so just recall, the sine of negative x is equal to the negative sine of x because sine is an odd function, not because you're factoring out a negative 1 from the angle, and cosine of negative x is equal to the cosine of x because cosine is an even function. Okay, you'll need those 2 along the way here. But when you're done, you're going to get something pretty nice, and you can check the textbook for you to see if your answer is correct. It's not going to show you the steps, which is what I want to see when you come to class, but it's going to show you the final answer. Okay, so finish that, and also finish or send me 2 questions via email that you had in the lecture, and we'll see you soon. Bye-bye.